What we're going to do is we're going to take a look at this as an example, expand upon it. So the business model, first of all, that they had, from your reading, was that they had options, right? What were their options that they can make? What were the options? Fancy versus sport skateboard. Okay? Sporty, sorry. And the things that were important here for the business model was if they were gluten pressed, the shaping, the trucks themselves, and recognizing that we have some limitations to our resources. That's one of your constraints automatically. Now, the data that was presented in this was that the profit from these two types of skateboards was different, but the time it took was also different. So before you even read and before you began, you should have probably looked at this already and said to yourself, so I make more money on the fancy ones, but it takes triple the time. So right off the bat, you knew your answer should have been sporty, actually, because look, you don't make triple the money. What should this number be if it was triple 15? 45. Yeah, if this was 45 and 15, and this was 15 and 5, this is triple the time. If you make triple the money, then it's a break even, right? You see what I'm saying right off the bat? Without even optimization, without Excel, you should be able to see that logically. If this was a number like 80, right? To go from 15 to 80, you're making like 6 times the profit almost. Well, it only takes 3 times as long to make it. So it makes more sense to make the one that gives you 6 times as much profit if it only takes half as much, or not half as much, but 3 times as much time to make it instead of 6 times as much. So you can think about that already. The shaping time is something that you want to minimize. Really, right? Shaping time needs to be under a certain value. Whereas the profit, what do you want to do with that? What do you want to do with the profit? Yeah, so what is the term for that? Increase. What's the term for that? Not minimize. Maximize. Come on, I just used the word minimize, right? I said you want to minimize the shaping time, so you want to maximize the profit you're making. So we have to start thinking about this. Now, you read this. What was your objective function? What was your objective function? What's the objective function? What's the overall thing you're trying to do here? And?
Z equals 15x1 plus 35x2.
Yeah, he said z equals 15x1 plus 35x2. Well, what he's trying to optimize, or in this case, is the objective function here, is the profit function. You make $15 profit for the first type, that's 15x1. You make $35 profit for the second type, that's 35x2. Think back to your math course freshman year. If you wanted to see how much money you made in revenue by selling tickets, you did these problems all the time. It was 2 variables, 2 equations. You always did it with substitution method or elimination method in your math course. Sometimes if you use the matrix. So that's what your goal is here. You're trying to figure out what you can maximize, or what you have to maximize, which is profit. Your limiting factors, there's several limiting factors here, and we're going to keep adding more limiting factors as we go on, recognizing that it's more difficult to find the solution by hand, which is why you would then go to some sort of a solving algorithm. All right, so first, decision variables. Decision variables. What are the decision variables here? What are the decision variables? Sam?
Where X1 is the production rate of the sporting brands and X2 is
Fancy. That's exactly right. X1 and X2. Number of sporty brand, number of fancy brand. So right away your decision variables are X1 and X2. Now, Anthony already told us the second part, right? He told us, okay, you know what? If the sporty brand is X1 and the fancy brand is X2, well, we make $15 for every sporty one and $35 for every fancy one. So that's going to equal the total profit, which in math we actually call the objective function Z. Okay, I'm hoping you're all looking at what I'm looking at, right? Yes? Okay. You're intently looking at your computers like there could be something else going on. I really hope you're focusing. So this is your objective function that we're looking at here. Now, what about constraints? What about constraints? What do we have? Chris, what do you got? Time. So do you have an equation for a constraint in this case yet?
It was like the inequality was like it has to be less than 2,400.
It gave you a number, right? When you're reading through, it told you how many days and how many hours you can work in a week and the shaping time per board. How much time did it take to shape the sporty board? How much time to shape the sporty board? It was 5 minutes for the sporty board. How much time did it take to shape the fancy board? 15 minutes. And what did we want to stay under? We wanted to stay under a certain amount of time. How much time was that? 2,400 units? Minutes. Why did you have to convert to minutes? 40-hour work week, right? Why do we have to convert this to minutes? Why minutes? Sam, you had your hand up first. You know what? Help her out, Klaus.
Because like the production of each unit is measured in minutes.
Yes. This is measured in minutes, right? 5 minutes and 15 minutes. If these were like a half an hour and 1 hour, these units would be hours. Remember in physics you had the dimensions that to match up? Same thing here. These are measured in minutes each, 5 and 15 respectively. That has to be in minutes. So that's your inequality. Any other inequalities? Any other? Caroline?
Needs to be non-negative.
Non-negative. What does that mean, Caroline?
Means that x1 and x2 have to be above 0 or greater than 0.
Absolutely. You can't have a negative amount of produced items. You can't produce a negative amount of items, pretty much. So those are your non-negativity constraints. That occurs a lot, non-negative constraints, actually. And when you go to Excel, what's cool, I think there's a feature, if I recall correctly, that all you have to do is check a box. And it makes sure that all of your decision variables cannot be negative. You don't have to set up all the constraints for every decision variable. Because how many decision variables do we have here, guys? How many? 2. In real life, there's like thousands in one problem. When you think about airlines and when there's a cancellation in a flight, have you ever been frustrated by that? Well, they have a linear optimization program running with like 30 million decision variables. Those decision variables are absurd, and they have to optimize them all. So as a result, you can't have like a program that you have to enter every constraint. So you have a non-negative constraint in general. Okay? Simplifies things for you. All right. So we have this already. I'm just going to fly through this because this is what we were talking about. Okay, x1 and x2 are our decision variables. We want to maximize our profit. If you confused you on the last one, it's $15 per sporty times the number of sporties. Well, what happens? What happens to the unit of sporty, which is a weird word to say? Yeah, they cancel out. Go back to physics. Cancel out. What are you left with? You're left with dollars. Dollars and dollars. So this equation is all about profit, or dollars. Those are the units for this equation. For this next one here, we obviously know that this is time. This is 5 minutes per sporty times the number of sporties. Again, canceling. Fancy, canceling. Leaving you with minutes, minutes, and minutes. The same units for all three. Does this make sense so far? Yes? No? Maybe so? I need to know if this is confusing, because it's going to get more confusing as we go through, or more, not more confusing, but it's going to get more detailed, okay, as we go through. And then finally, the non-negative constraints here at the bottom. So this is our overall summary that we were looking at a moment ago. So we want to maximize one thing subject to 3 constraints. 3 constraints. So now that we did Excel, let's jump to the next constraint. Now, what we can do is look at this next actual inequality we're seeing here. What does this inequality look like to you? Where did that come from? Any idea? Any idea where that inequality came from? I know it's an inequality because it's shaded, right? You see it's all shaded under here? This is shaded. Remember when you graphed inequalities in math? You would put a dashed line or a whole line, and then you'd shade one side of the actual line. Sam?
I feel like this seems like an being less than or equal to 6,000.
Yes, this is your constraint, less than or equal to 2,400. If you look at that equation, go back to that equation, please. I'm going to pause. We're looking at the other corner. Yeah, but that was good. That's the intuition you wanted there. It's 480. This is the first one. This is the second one. So this solid blue line is your time constraint. And what did it say? It should be less than or equal to 2,400. So when you shade, you're shading below the line. If you didn't know to shade below the line, to test, you pick a point below the line and a point above. If it's true, when you plug it into the inequality, you shade that side. So if I pick this point right here, 50, 50, plug it into constraint. 50 times 5 plus 50 times 15. Is that less than or equal to 2,400? It absolutely is. Therefore, you shade this side of the line here. This is a graphical representation of optimization with a simple example because we only have 2 variables, right? The minute we have a third decision variable, it becomes a 3-dimensional, what's called contour plot. The minute you have a 4th decision variable, you can't graph it. Okay, it's impossible to actually graph at that point. So this is just the very beginning idea or picture of what we're going to do with this project. And that's cool. Why are these acting as boundaries? Why are the horizontal and vertical axes, I should use those terms instead of x and y. Why do they act as boundaries?
Because it can't be negative.
Non-negative constraint, right? Now over here, would one of the numbers be negative? x1 would be negative over here, and what would be negative down here? x2 would be negative down here. So these three quadrants are not included. So we have what looks like here a polygon. Now, on the next page in your reading, what did it tell you about? When you're looking for the best solution, what do you look for? Corner points. There's something called the corner point theorem, actually, that actually proves that the corner points are where you can get your maximum or your minimum values always. So in this case, how many corner points do we have? Three. One of them clearly gives me what? If I produce 0 and 0, do I get any profit?
No.
So doesn't this do what? What does this do?
Nothing.
It gives me the what? Profit. Fill in the blank.
Baseline.
Zero.
Minimum. Minimum. Baseline, 0, minimum, really. This is the minimum point, actually. But what do we want?
Actually, if you
We
burn
want
mine,
maximum.
that's the minimum.
We want the maximum. So we test the other two corner points now, or vertices. And that's on the next slide where you're going to see here. So we test the corner points. It looks like the 480, 0 corner point gives you the most profit, which tells you what Koenig was complaining about. He said, oh, nobody makes any fancy ones. What if I want a fancy one? I told him, go to another company. He's claiming this company doesn't care about fancy ones, based on this analysis. Okay, so these are your corner points here, and your goal, again, is to maximize. That's the objective function right there. Questions so far? I'm going to stop and go to Excel to use this as an example because it's very simple. Because then we're going to do ones with like 5, 6, 7 decision variables and allow Excel to help us solve it. Okay? So I'm going to pause at this point. We're going to go to Excel, but I want this. Here's our optimal solution. Here's our optimal solution, $7,200 profit. Let's go to the next constraint now that we used Excel to see this. Okay? I'm going to skip these questions. We already talked about it a lot. Hey, by the way, remember my first statement? In the very beginning, read it. Wow. Fancy is not 3 times as profitable, and it takes 3 times as much time. So we knew right away that it's got to be all sporty. That was the whole idea here. This is the reason why you could have seen this without even using Solver. Okay? All right, so let's add a new constraint. The new constraint we have is a limited supply of trucks. We're only allowed to get 2,800 trucks per month, which means 700 trucks every week. And each board requires 2 trucks. So we take a look at our inequality here. We see that it takes 2 trucks for a sporty times the number of sporties, plus 2 trucks for a fancy times the number of fancies. And that has to be less than 700 trucks.
This makes it way more complicated.
Okay, now you have another inequality, a completely different inequality or another constraint. So take a look at our new analysis here. We have this added constraint of 2x1 plus 2x2 less than or equal to 700. Again, 2 trucks for the first one, 2 trucks for every fancy one, meaning less than the total amount available of 700. Take a look at this new constraint now. It's in purple. Look at the purple constraint. That limits my feasible solution range now big time. Where was the solution last time? What was the answer again? Who knows? What was it? It was 480. It was right here. Is that in the feasible region anymore? No, it's not. So the feasible region has to be less than this inequality, but less than this one also. To be less than this one, it can't be in this little triangular region on the right. Again, this little triangular region here is no longer part of the feasible solution because this is the truck, the amount of wheels and trucks that go on there, limitation has to be less than. So we have 1, 2, 3, 4. Do I need to test 0, 0? No, I don't have to test 0, 0. Okay? But you do have to test this region. We did it last time. You probably have it already. This point and this point are new points. Test them also. If we test them and we take a look, we see now that we have a new answer. 285 sporty and 65 fancy. Okay, that is our optimal solution. Can we jump to Excel now and add this constraint in? Okay, it's pretty simple. Okay, let's add the constraint into Excel. So it's going to be 2x1 plus 2x2 less. So now, we'll take a look at an example that has a limited supply of North American maple veneer. So there are 840 North American maple veneers per week. Each fancy board requires 7 North American maple. In each fancy board. So how do we set this up as a constraint? How do we write this? I mean, it's written for you here, but how would I think about this as variables? What would the variables turn into in this case? And try not to look ahead, please. Just look at this slide so you can see what you're doing. Again, 840 North American available per week. Every fancy board requires 7. So there are 7 North American veneers per fancy board, times the number of fancy boards, which will tell you how many North American veneers are needed. And there are a total of 840 North American veneers. Why is this a 0 here? Yeah, it doesn't say anything about needing North American maple for the sporty board. So no North American maple is needed for sporty, so this is not part of it. Class?
Wasn't the number of fancy boards 0? So like the whole thing would be 0?
If for the original solution with one constraint, that was the optimal solution. But now, when we add a new constraint, we don't even know what the solution is. So we can't assume it's 0. It's a great question, though. Remember the first solution, the answer was like, make 480 sporty and no fancy boards? Yes, for that solution, it wouldn't be usable. It wouldn't even matter. But what we're saying now is we now have the truck constraint from the last part, and now, in addition, a third constraint of North American veneer. So we have to assume that we don't know what the optimal, and the optimal won't turn out to be 0. But my question is, how do I write this as an inequality, people, with variables? Oops. Oops. Less than or equal to? What about the x1? You have to put it? 0. Okay, so if you want to write this here, you can, just so you know what you're doing, but you don't need the 0. There are no sporty boards, no veneers used for sporty boards, North American, and there are 7 for every fancy board. And you need to have less than 840 used because you get 840 shipped in every week. All right, so now what does this do again? What does this do? Physically, what is this doing? What is it doing by adding a third constraint now? What are we actually doing to the problem? Yeah?
Is that the limit? So you can't go over 340?
Good. We're setting another constraint or another limit. What does that do to our feasible region? Our feasible region, what's it going to do to that?
That makes it small.
It's going to make it smaller. It's going to cut out part of the feasible region. It's definitely not going to increase the feasible region because it can't increase as you add constraints. It can only decrease. So let's take a... So here's our constraints now. Notice again, here's the new constraint in case you don't see it. There it is. That's what Chris just mentioned. So we've got, again, time constraint, truck limit constraint, and North American veneer constraint. Veneer? Is that how you say it? Veneer? The one? And they have to both be positive still at the end. Nothing else has changed. Look at your profit. Your profit function is still 15x1 and 35x2. Why? Why does the profit function remain the same the entire problem? Why doesn't that ever change? Remember, your goal is to maximize profit. Why is my profit function not changing yet? My constraints are changing. What's happening in this problem? Why is the profit function not changing? Not changing. Here's an answer to the last couple. So what about you guys over here? How come the profit function isn't changing? Notice again, this was the time constraint started, right? We have a solution. And yesterday or the other day we added a truck constraint, got a different solution. Now we're adding a constraint for the type of wood that can be used. But this has never changed. Why hasn't this changed? Where is this coming from? This comes from a specific location in your slides. We talked about this right here. Where did this profit function come from in the first place? You don't remember? Larry. Nick?
Well, I was just going to say that it doesn't matter what the profit formula is always going to stay the same. It's just the numbers you plug in are going to change to x1 and x2.
Okay, so Nick is saying x1 and x2 are the things that are changing. Absolutely. That's the things that are changing.
Those are the prices of the actual boards. So
This is what is 15? The amount of
sporty. It's the price of the sporty boards, right?
the price, the profit per sporting board. You want to say price, the price is different. The profit made per sporting board. What is this?
Profit made
For fancy board. Remember, the profit is what we're trying to maximize. The amount of money you make per board is not changing. This is the amount of money made for each board. It doesn't change at all. The amount of boards you produce, X1 and X2, are what are changing. And obviously, as we add more constraints, we have more inequalities. So we go ahead and we take a look. Now look at our feasible region. Earlier, we did not have this North American maple line. So imagine the North American maple line isn't there. The feasible region actually continued, let's see, it continued all the way through. Actually, let's see, did this limit us? Oh yeah, it cut out this region right here. This is the region that it cut out. Okay, that region earlier was one of our feasible solutions still, right here, this top left triangle. It's no longer there. Okay, again, it's all cut out in this case. This was here a moment ago, and now this is no longer a possible feasible solution.
Didn't we find that the second constraint at 285, 65 was the most efficient?
It did for the last one. Do you think it's going to be the same for this one?
Why wouldn't it be?
Well, now we have 1, 2, 3, 4, 5 vertices to test.
But that point's still there, and the 120, 120 point was there in the last version too, so I don't care why I would change.
You're making great intuition, Nick, and you're absolutely right. I want to hear you explain it, though, a little bit better to the class so others can understand that. Nick is saying that this is going to remain the answer. Explain why, Nick.
Wait, say again?
I said, you just said that this is going to be the answer again. Explain why.
So, it was the,
You want me to go back to the slide so you can see?
well,
To compare?
sure. 65 was the point that gave us the most amount of money last time around, and it's still here. And the only point that's been added is the 120, 120 point and the 0, 120 point. But those were there in the last time too. So there's no reason it would change from 2.
Think back to that's exactly right. Think back to the last one. This was also shaded. So imagine this is still shaded here, okay? Now, when this was shaded, the possible solutions were 1, 2, 3, 4. That was it. This wasn't even one of our endpoints or corner points at all. And neither was this. So these 2 corner points are now here as a result of this constraint. Well, these 2 corner points were in the feasible region earlier too. So by default, we kind of tested them already. So these corner points are not going to produce a greater profit than this one that we had in the previous slide. Very good, Nick. Well done there. So we're going to take a look and see where's our answer. We can see again, it's still 285, 65. Here's the new corner point that was produced, 120, 120. That's the one Nick was mentioning. And again, as he noticed, he said, it's got to be less than this one because this was in our feasible region earlier and it wasn't the optimal solution. This was. So 6550 is remaining to be our optimal solution. Any questions on that other constraint? We're going to do one more of those, then I'll go right to Excel. This is what you were mentioning, Nick. It's the same as before. So this maple constraint is non-binding. And the way you can actually see that, I'm going to pull up Excel in a moment, and in Excel, if you remember, you can see the amount of parts that are used and the actual maximum, or the amount of time that's used and the actual maximum. When those 2 numbers aren't the same, you say that it's non-binding, okay? Meaning that the North American constraint is not met. You're not going to run out, or you're not going to use up all of your North American maple, veneer, whatever they're called. All right. So let's take a look at a 4th constraint now. So let's say that there are these veneers that come from China, and they're used for the sporty boards. And every week you can get around 1,470 of them, and 7 of these are used for each sporty board. What does that equation become, or that inequality? Tell me what the new inequality is as a result. You can look here to see, but base this off of the last idea as well. How would you base this off of the last idea as well? Again, X1 is the number of sporty boards, and X2 is the number of fancy boards. What would the new constraint be? It's the same people raising their hands. Come on. There are others in the room too. There are a couple others that I keep looking at that need to participate a little bit. 7 veneers per sporty board times the number of sporty boards. No Chinese veneers per fancy board times the number of fancy boards equals the total amount of veneers available or possible. So literally, what do we have to write down?
7x1 plus 0, P1, and it's less than or greater to 1,407.
Less than or greater than? What did you say?
Oh, less than or equal.
There you go. Like, how could it be less than or greater than? Yeah, exactly right. Again, 7 of these veneers per sporty board. X1 is the number of sporty boards. No veneers for the from China for the fancy ones times the amount of fancy boards. This doesn't matter. Drops off. So all this does again is it adds another constraint. Take a look, please. This was the time constraint. This, again, was the truck limit constraint. North American veneer for the fancy boards. Chinese veneer for the sporty boards. And they have limitations to each of them. So again, this is going to introduce another line on our feasible region. Think about this for a second, please, and visualize. Look up for a sec. Visualize. The last constraint that we added, the North American constraint, if you recall, it was a horizontal line. Right? It was a horizontal line. And that horizontal line cut across at a certain location. That was when we were looking at variable x2. Now we're looking at variable x1. What do you suppose this next line would look like? What do you suppose this next line would look like? Vertical line. It's going to be a vertical line that limits my amount. Think about it for a second. Again, your axes are really x1 and x2. So if I take a look at this now, see the Chinese maple constraint? See how it's vertical here? It's not a coincidence that it's a vertical line. It's because the equation for that came from the fact that we had, again, I'll write it down so you can see it. This equation for Chinese maple was 7x1 less than or equal to, what was it on the previous slide? Just read it to me.
1470.
Thank you. Take 1470 divided by 7.
210.
What do you get?
210.
How do you know it's 210?
Because 14 divided by 7.
Oh, I thought you just saw it on the graph also. Look at the graph. Look at the coordinates, guys. The coordinate for x1, what are the coordinates? 210 for both of these points, right? This is not a coincidence that it's a vertical line because it's only one of the variables. Think back to your math course. Y equals 7 is a horizontal line that cuts across 7. X equals negative 4 is a vertical line that cuts through negative 4. Your x equals and your y equals were vertical and horizontal lines. That's what makes these constraints vertical and horizontal constraints now. So, where is it? Nick, tell us, is it going to be the same answer again?
No.
How do you know right away, Nick?
It's gone.
Yeah, it's gone. The last answer was right here. This is where it was. Take a look. This was your answer. 285, 65, something like that. Well, it's no longer even in the feasible region. So this new constraint that we're applying creates new endpoints. 1, 2, 3, 4 that need to be tested. I don't have to test the origin. That will minimize. So these 4 need to be tested in the profit function. So we go to the profit function again. We take a look at the profit function. We test those 4 points. Turns out that this is now our new optimal solution. Okay, again, whichever of these 4 corner points is the best solution gives us the optimal solution. So the project I'm going to give you on this will definitely be using Excel, but I'm going to probably bug you enough with maybe a 2-variable example on how you do this by hand. So I guess that you can do it by hand also. So by creating your graphs, drawing each of your lines, finding the corner points, testing the corner points. Okay, so I'm probably going to bug you to do that by hand as well. I want to see that you understand what we've been talking about, not just sitting there going like this the whole time. Okay, so this is the optimal solution now. Let's see if there's anything else. All right, so this was adding a 3rd decision variable. Nick, this is the question answering yours about having more than 2 variables and not being able to graph it. So adding a 3rd decision variable. Having something that earns $20 profit, takes 4 minutes of shaping time, takes 2 trucks every time to be made, and 7 Chinese maple veneers. So it's a little bit different. It makes more profit than one of the other ones, takes a different amount of time, all this stuff. What would that look like suddenly? You'd have a new decision variable. That's decision variable number 3. So we've had sporty and fancy all along, and now we have pool runner boards. Carolyn?
What if, like, people might be practicing?
Yeah. So here's our third decision variable, x3. Okay, so this is what it would now look like with 3 decision variables. Let's go back and go through everything, right? I'm going to point to each of these. If you don't understand, make sure you're focusing and listening to all of these, Nightman, please. So the 15 here, 15 comes from profit for each sporty board. Profit for each fancy board. profit for the new board that we're now introducing. It was 5 minutes to make a sporty board, 15 minutes for a fancy board. Now the new one we're introducing takes 4 minutes to shape, but we still have a certain limit of 2,400 minutes. It takes 2 trucks for all of these, which makes sense. Actually, there's no such thing as a skateboard with less than 2 trucks, right? I've seen new ones that are like odd looking and stuff, but not 4 wheels, right? Aren't there ones that have fewer than 4 wheels now and stuff?
There's like one wheel, it's a big tire.
It's like a 1-wheel thing, yeah. But there's always 2 trucks still, right?
Wait,
And on a regular skateboard.
It's the metal on the bottom of the skateboard, not trucks. You thought it was trucks like carrying stuff? Oh, that's hysterical. Yeah, the truck's the thing that holds the wheels on the bottom of the skateboard. I didn't define that till just a moment ago, actually. So it takes 7 North American veneer to make one of the fancy boards, and you have a limit of 840 North American. It takes 7 Chinese veneer and 7 Chinese veneer for each of the sporty and the pool runner, whatever that was called, and you still have a limit of this amount. So what have you done? You've introduced a whole new type of board, a whole new type of a production. So you're going to have now an answer that is an answer for X1, X2, and X3. So the optimal point here for, and we'll go to Excel right now to see this. The optimal point here for this is going to be 3 coordinates. So let's take a look at that.